Alright, hey and welcome to episode example 10, sorry. In this one we're gonna take a look at something a little bit more advanced. We're gonna take a look at how to make a fake RBD impact. So we basically gonna use a bunch of geometry, a bunch of pieces. We're gonna make some kind of ground hit where like the earth or the ground or some kind of stone or something is shattered and exploded into the air. It's gonna look kind of like this. This is a low-res pieces, so it's not so much detail to it, but it's still like the physics and the actual idea of it. So let's play it. So it's gonna look kind of like that. We're gonna like to look at a couple of attributes here: how to get them to spin, how to get velocities right, how to get the pieces right, how to get different pieces onto different points, and yeah, a lot of useful things in this tutorial. So it's gonna be a longer one, but hopefully it's gonna be very interesting. So yeah, I'm gonna manage this. So we have a couple of parts here. We have a source, we have our velocities and orient, we have our particle system, we have our p-scales and type attributes, and here we have the actual geometry manipulation. So I'm gonna start off on this branch, and once we get here, I'm gonna jump over here and take all of this, and then we're gonna go do the copy and the rest of the tutorial. Okay. So first of all, the source is very similar to example 8. You're just going to do a sphere, some mountain to get some noise in it. And this we're going to transform it down. So we put the y value to 0. I can show it that by using a constant. So the new vector is x, z, and the y value is 0. We put this position like that. Then we scatter points on that. We put it to like a 420 points. We click off relax iterations to make it faster. Next up, we're gonna initialize some normals. Doesn't really matter the value. I just want the normal on each point. So I added a point sub, and I've added add normal, and I put the normal to 1, 1, 1. Next up, we are gonna create some velocities for each point. And to do the velocities here, so I'm gonna use a very similar technique to what we did in example 8. Just really randomize it. In this one, I kind of multiplied the y value by a little bit more. So it's the same here. It goes to the terminal noise. Here we have the offset. We can change the offset. The frequency is at 5. Signature is 3D noise. Noise type is sparse convolution. As we remember, sparse convolution goes from 1 to -1. So we have to correct that later on here. We pipe the noise into a vector to float because we want to manipulate the y value to be positive. The other x and z value goes straight into the float vector here. The y value goes down to an absolute, which makes every minus value a positive one. So if the minus value is -0.1 for a point, it goes to 0.1. And it goes back to y. So to add some more values to the y velocities, I've done an add after absolute, and in the add I've also added in this string that is going from ptnum, that is random, which outputs a value between 0 and 1 for each point. That goes into the fit. In the fit, I've just put 2 different values here. That is going to be numbered out on every point, so every point is going to have different value between 1 and 2, which we add onto this, which means that the absolute is going to get added onto a value between 1 and 2, and that's going to get added back in the float vector here. So as you can see, the y-axis gets a little bit longer, elongated, which is nice because that's what we want. We want a little bit more push in y for this velocity. The vector I'm going to output to normal and to the velocity, just because I like it. I like to visualize it with the normal in the viewport, like this. But you can easily click this off if you don't want it. Anyway, so that's it for the velocity. Next up, we're gonna create a new attribute here that we never really talked about, that is called an orient. So an orient already exists for every particle, and it looks something like this. Orient you can visualize in the viewport as well by clicking this little thing, which is like a ball with 3 axes on it, and it looks interesting. Okay, here we go. Yeah, something was wrong. Anyway, the orient is always created, and it's really, here is kind of uniform. As you can see, all the vectors are pointing upwards. Orient is an attribute that is actually a quaternion, or a vector 4. So it has not only a y, x, and z value, it has also a, if you think of it as a color, it has an alpha vector as well. So it has a R, G, and B, and A, which means that it can also take in rotation, which is really useful because that's what we want in these points. So we want to kind of rotate them. I first of all want to make a random orient for each point, because if you only do this and then go ahead and copy things onto them, let's see how it looks. Everything is going to point the same direction, which we don't want. We want to have a really random orient, which we can get. So now, as you see, all everything is pointing upwards. If you untick this, everything is really random and like randomized. So if you go into the orient, I've done some things here. This is kind of over course, like a little bit too advanced for this series, I think. But we are gonna do some matrix to quaternion manipulation here. I want to rotate these orients, and I do that with an align that goes from the normal. It takes a normal and it takes another vector that's up that I've just made from 0, 1, 0. So it kind of aligns those, and it takes a matrix and it creates a matrix. The matrix going into rotate, and the rotate I can rotate with any angle here. The angle is a it's not a degree, it's a radian, right? Radian. But yeah, I can kind of rotate it, as you can see, with these values. So I can rotate all the points here. I've kind of done ptnum to random to get a 0 to 1 value that goes into fit. So I randomize the rotation as well. So some points get rotated 0 radians, while some get rotated 10 radians, which is a lot. But I can rotate it more. As you can see, they keep on rotating. Anyway, and the rotate outputs a matrix. We don't want a matrix because we want to use a quaternion. That means we need to convert our matrix to a quaternion, and we're going to do that with a matrix to quaternion, or matrix to quat. We pipe the matrix to the matrix input, and out comes a quaternion, and we output that to a bind. Call it orient. And the orient has to be a vector 4 or a vector 4 floats. And then we have an orient here updated. So before it was like this, now it's like this. Really randomized and nice. Next up, we're gonna start simulating these points. So let's switch these off. The orient values. We have our velocities and we have our orients. So in the popnet, I've done a couple of things here as well. I've done the birth fix from example 8. I've done the just born group, this. I've done an emission type all points, and I've done an impulse activation. So everything that is before frame 3 is emitted. So on 1 and 2, points are emitted, but after that, nothing is emitted. The life is put to 100 because I don't really want anything to die, so I put it to excess amount here. But anyway, because RGBs, like nothing would die, because they would just keep on being solid objects, right? So anyway, so I've done a just birth group here. With the just birth group, I have done pop-up, where I put the group to be birth, and in here I've kind of corrected the y value for the position, like that. Yes, we did in the source actually for this point. And it goes back to the position and kind of correct it. So without this, it would look like this, and now it looks like this. Just to get them back to the ground plane. Next up, we want to add some velocities in the rotation, which is called angular velocity. And the angular velocity is actually its own attribute, and we could have set it with outside of the pop system, but I want to add a pop torque, which keeps on adding angular velocity to them. So the angular velocity is signified by the W attribute. It's written like this. So it's at W. And the velocity, as we remember, is called at V. So angular and velocity, basically. Okay, let's take this off. So I've added a pop torque for each axis. I've added a pop torque in axis X, axis Y, and axis Z. And I've set them all to 5. Now, if we do this, it's gonna keep on spinning unlimited. Like if you turn this on and we turn this one off, we can see here that when we actually simulate, they're gonna start spinning, and then they keep on spinning once they hit the ground plane. We need to correct this. We need to add some values that kind of modifies this, so we don't have them spinning forever. This is a little bit tricky as well, but we're gonna do it in a pop VOP here. And we want to limit it. And we have a really cool attribute for that called spin max, which kind of says that this is the maximum radians a point can spin per second, basically. You can set this with a speed limit here, and you can do a maximum spin. But we don't really want that because it's going to be a solid value, which is going to be for everything, and we can't really modify it based on age or anything like this. But we can see here that the parameter or the attribute is called spin max, as you can see here. But we want to do it by ourselves. So basically, we need to create this attribute called spin max. Spin max is a vector. No, spin max is a float. Sorry. Spin max is a float, and it only says how many radians particles can spin per second. So if you go from, if you have 100, you can spin 100 radians per second. If it has a 0, it can spin 0 radians per second. So we kind of want to go from a really high radians per second to a really low. And once they hit the ground plane, we want to have a 0 because we don't want it to spin on the ground. Okay? So how do we do this? Well, first of all, we need to limit it by age. Okay? So I want to do this. I want to say that I take the age of the particles from here, I put into a fit. I say it's gonna go from 0 to age 2. So 2 seconds, I'm gonna think of these particles. It's gonna go from 100 radians per second to 0.1 radians per second. And basically, this means that it's going to get multiplied here, and it's going to go into spin max. So we now have the values from 100 to 0.1 in the spin max. Therefore, we kind of want as well, we want some other parameters to modify this, which means that we want to take our ID, we want to put it to a random, which means we're going to output a 0 to a 1 value, and we put it to a fit that goes from 0 to 10. This means that we can modify it even more, right, randomly per particle. So now we're multiplying this by this, which means that it's now really randomized per particle. Okay, so that's cool. We have our actual values here. We have our 100 to 0.1 per age. We have a randomized value here that we kind of multiply it with, and now we also want to limit it. So when it gets lower, or when it actually becomes closer to the ground plane, we want to limit it to not spin at all. So how can we do this? We can do it with a ramp, but I'm going to do it in a pretty dirty way here. So I'm just going to do a position to a vector to float. And we want to look at the y value here. So we're going to pipe the y value into a compare and say if it's greater than 0.1, which means that if it's greater than in 0.1 in y value, it's going to get the Boolean value of 1. If it's less than that, or if it's less than 0.1, it's going to get the Boolean value of 0, which means we can multiply all of these values here with either 1 or 0 based on the position in y of the particle. So I'm going to pipe this into here. And this means that any value here we have is going to get multiplied by either 1 or 0 based on the y position. So if they fly here, and once they get closer to the ground, let's take this particle. It's probably not 0.1 in y value yet. It's probably more than that. I guess it's a 1 here actually, or maybe even 5 or something like that. Once it's flying closer to the ground here, it suddenly is going to get a value from this one of 0 instead of 1, because it's a threshold. It's lower than 0.1. Therefore, all these values are going to get multiplied by 0, and the output value is going to get 0. So once they get lower, they get a 0, which means they will be dampened and suddenly stop spinning. Or, yeah. It's a bit convoluted, but I urge you guys to take a look at this scene file to really like see what happens when you unplug things and cannot see what's going on. I'm trying to explain it the best way I can, but it's kind of my thinking here. I want to first set a value, then randomize it a bit, and then limit it. So I have a 3-step thing for my spin max to work. Anyway, so this is it for the torque and the spin limiting. Then we just add some turbulence with this. I kind of want to limit the turbulence to just the first couple of frames, so I've kind of done it by age. I've kind of piped the age into the amplitude with a fit in between, which means that if the age is 0, it's going to have a turbulence of 5. The amplitude is going to be 5. If it has an age of 0.1, the turbulence is going to be 0. The amplitude is going to be 0, sorry. And in here, I put it to 3D noise, sparse convolution noise, and frequency to 3.2. I've added it back to the position, so I've done an add. I first added I've added to the velocity actually. So I've done the velocity in the first input, and the second input I've put the turbulent noise to the input, which means that we're gonna add this onto the original velocity, which means that we're gonna break up the original velocity a little bit, make it a little bit turbulent, and just for the first couple of frames. And we pipe that out to velocity, and that's all good. Next up, we're gonna add up gravity. In this case, we don't want to use the original gravity because I want to do some custom things to it as well. Gravity is a force. Gravity is usually 0 minus 9.8 0 in the vector, and here I also want to get the option of multiplying this. So I kind of decided to do this in a pop-up, which means that we're gonna first take a constant, put it to 0, minus 9.82 and 0, and then a multiply. And in the multiply, we're gonna put a parameter. And we're gonna put this into the force. With the parameter here, we can go up here and actually multiply it. So if you want the gravity to be double, we can put it to 2. If you want it to be normal, we put it to 1. Next up, we have the friction. This is for when the particles actually hit the ground plane. So we want some randomness in the friction as well. And I'm telling you, randomness is always good. Randomness is gonna make your simulations look really organic and actually believable. So randomness is great. We're gonna take randomness in this by the ID. So we're gonna take ID, put it to a random, which means we get a 0 to 1 value coming out of the random. We pipe that to a fit. In the fit, we're gonna put 0.3 to 1, which means that our friction value for each particle is gonna have a value between 0.3 to 1, but really randomized. Then we can multiply that. I haven't done that. I've just put a 1 here, but we can multiply it, and then we put that out to a friction, which is a float value called friction. And yeah, that's basically it for the particle system. In the particle system, we also have a ground plane to make some collisions, same as example 8. I've lowered the bounce a little bit. Maybe we should lower it even more, because RBDs doesn't bounce that much, to be honest. And yeah, that's it. Let's take a look. There's an infinite plane. You know, turn it off like that. That's it for a popnet. Next up, we're gonna modify the p-scale. But first, we can take a look at what the actual particle simulation looks like with our orients on. So it flies, it spins, it kind of bounces a bit, but it stops spinning, as you can see. So they spin, but they stop spinning, which is exactly what we want. So that's great. Next up, we're gonna do the p-scale of this. In the p-scale, we want to kind of like a randomized p-scale, but we really want it to be a controlled randomization. So usually when you work with these kind of things, you want a lot of small particles and a couple of bigger elements, bigger particles, which is why I've done this. So to randomize the p-scale, we kind of want to fit the PT num. by how many the number of points, okay? So we want a 0 to 1 value for each point in here, okay? To do that, we take the ptnum, we put the value in fit, and in the source max, we put the numbers of the point. And therefore we get the source min to 0 and the source max to the last point, basically. This also means that in our ramp, we get a 0 to 1 value, which means that we can now control the p-scale and the kind of distribution with the ramp, which is awesome. We're also going to put a multiply and put a parameter to it, which makes our lives easier if you want to multiply this p-scale, if you want to make things bigger or smaller, just a uniformly multiplier, basically. And we're going to output to a bind with a p-scale set to float. So in the ramp, we kind of want to put it to this kind of ramp, which means that a lot of small particles, and suddenly they become bigger and bigger and bigger and bigger. So we have a little amount of big pieces, while we have a big amount of small pieces. So that's basically the philosophy for my p-scale in this sense. Next up, we have the type attribute. This is a custom attribute. This is nothing that exists to begin with. And I'm going to use this because I want to be able to randomize the copied on pieces to my points. So basically, just taking a look, short peek over here, we're going to shatter a block here, and we're going to have these pieces, separate pieces, a couple of random looking ones, a couple of different ones, and I want to be able to have a random distribution of these on my points later on. And to make this happen, we kind of need to create a couple of attributes here, and one of them is a type attribute. I'll call it type because I think that's a good name for it, but yeah. So basically, one thing I need to know is how many pieces am I gonna have, and this we can check out here. We're gonna have, basically we can control it with this. So if we have a scatter here in our box, this is a little bit, I'm jumping forward, but we need to know how many pieces how many different kind of pieces we want to have. And here we have 20 pieces because we have 20 points that is going into Warner fracture. Therefore, we want to limit our type attribute to be between the values of 0 and 19, an integer, which means that we have 20 variations of this number that goes from 0 to 19. So in our type attribute point swap here, we want to do some fit to do that. So we're gonna do a fit on the IDs of each particle. So we're gonna pipe the ID into the value of the fit, and to get the source maximum of the points, we're gonna pipe the num-pt, and the values is gonna go between, as I said, 0 and 19 because we have 20 points or 20 pieces that we want to randomize on it. We want to make these values coming out of the fit into an integer. So we're going to use a float to an integer, which makes that, which basically just like snips off the float values afterwards. And we're going to output that to a bind to a type called, to an attribute called type, to the type called integer. And we also want to make this a local variable because we need it later on here. Because HScript doesn't really like these kind of attributes. It likes having a $sign and a capital type. So we kind of have to do that with an attribute create. So we add an attribute create, we put the value to be at type, we put the name to be type, and we have to tick this box called local variable, and we put type in all caps. Now we're ready to copy these things on. First of all, I'm gonna go over the copy node, and then I'm gonna go over here. But in the copy node, we want to do a couple of things. We want to do some stamping, which is really interesting because you can basically use attributes from these points to modify the geometry over here. But the only stamping we're gonna use here is to randomize what piece gets copied onto what point. So we want to use our type attribute here. So if we go to the stamp tab and we put stamp inputs, and we also want to pack geometry before copying, We are gonna first, in the value, we're gonna type $, capital letters type. And we're gonna put the variable name to piece. Okay? This means that the piece variable is now also the same values as the type. So for each point, we now have a piece variable that can go from 0 to 19. So with this variable, we're now gonna stamp this input onto these points, and we can then delete geometries from here that we don't want. So if we want to do that, it's quite easy. We just need to use one of these stamp strings. But first of all, I'm gonna go over to do the geometry side here and kind of talk about what's going on here. So we kind of took a short sneak peek what this is going on here. Basically, I have a box that I do up to a volume. I do some noise. I do some scatter, some points, 20 points to get 20 pieces. I use a Voronoi fracture to just fracture this. Really simple. We're gonna do more of that when the RBD chapter is coming up here. But anyway, we can use an explode pieces to kind of visualize what's going on with our pieces, and it looks like this. So these are the pieces we want to copy onto the points later on. Next up, we want to make an attribute on each of these called class, and we want them for each one of these pieces. Okay, and an easy way to do that is to use the connectivity the connectivity sub, which basically will take everything that is connected and put an attribute called class. Class is a string. So when we put the class attribute here, we put the connectivity type to primitive, and we put the attribute to class. If you go over to the connectivity sub here and go to the geometry spreadsheet, we can see that the class is equal to 0. Sorry, the class is actually an integer, which is great because that's what we want. It also goes from 0 to 19 since we have 20 points. And this is great because now we're starting to kind of get matching attributes here. We have a type attribute from 0 to 19, and we have a class attribute from 0 to 19. And as you're gonna see later on, we're gonna use this and match them together. So if a point has a type attribute that is 0, it's gonna get the piece that has the class attribute that is 0. I'll explain later, but anyway, so we can visualize the connectivity here, or the class, just to see that it worked. So each point gets us a different color, and it seems to have worked fine. So that's great. Another thing that we want to take care of is to make our pivots of each point centered. So basically now, if you have a look here, the center of these points are all over the place. They are not 0, 0, 0. They can be a lot of different values, and we don't want that. We want each piece to be zeroed in, so it has a position that is 0, 0, 0, and we also want to pack it. So how we can do that is with another thing called a for each loop. This thing can be a little bit tricky to understand sometimes, but I will explain. So think of it as a thing that loops over each thing that has an attribute. So for example, the for each loop takes the class attribute by default. So if it recognizes that each piece here has a class attribute, it's going to recognize that and cannot think that, okay, I'm going to run whatever happens in here over each of the geometries that has a different class attribute. So basically here, if we click the first for each thing here, we can see that it has already made that thing. It has taken one of the pieces, and we're going to work on this piece now. So we want to make this piece first. We want to center our pivot to the piece, and then we want to transform the piece so that it has a position of 0, 0, 0. So first we're going to make, so if we check here with a transform really quick, just to see where our pivot is at now, we can see that our pivot is actually in the center, which is not good. We don't want that because the piece will spin all over the place, because pieces spin around their pivot. So if the pivot is here, it would be spinning like this, which is not what we want. We want it to spin around its own axis. So if we go to this transform node here, we can see that now we have actually centered the pivot to the center of this point by using this $CEX, $CEY, and $CEX. This is a H script that basically finds an expression that finds the center of the point of the primitive, which is really useful. It's great for this kind of things. So now we actually have centered our pivot, which is great. We want to pack it so we only have a single point. Okay, you have to check with the transform here. Where is our pivot now? It doesn't matter. Our point is centered, so it's fine. Anyway, and now we're gonna use this point up here to transform the position to 0, 0, 0 by doing this, which means that our piece is now in the center of the grid, which is great. This is exactly what we want. And now here the magic comes. So if you click the last for each node here, boom, it has done the same thing for each of the piece. For every piece that had a different class attribute, it has now transformed them to the center of the grid, which is exactly what we wanted. So now we're gonna unpack these pieces. Yes, because we need to do the next step. And here we go. Here's the magic. We're now gonna drop down the delete node, and we're gonna set delete non-selected. Because we're only gonna select a single piece here. We're gonna set the entity to primitives. We're gonna set the operation to delete by expression. And now we want to type a small stamp expression here. So as we know, we have a class attribute. So the class attribute ranges from 0 to 19. And we want to say that if a piece has a matching point, it's gonna copy on the same piece with the same class attribute. Which means that if the class here is 0, or sorry, if the stamp for a point here is 0, it's gonna grab the piece from up here that has the class attribute that is 0. It's a bit convoluted, but look into stamping attributes and look into that kind of stuff, and look more into that, and you will understand. For the stamp expression, we need to write stamp in parentheses these two quotation marks dot / copy, and we want to reference our copy node. So if the copy node is called copy 1, we want to type copy 1, but here it's called copy 3. So we're going to type copy 3, quotation mark, comma, quotation mark, piece, quotation mark. And piece, as we remember, is our variable that comes from the type attribute. Okay, we could, for easy's sake, we could type this to type. We could put the variable to type, and then we have to just change this to type, and that's fine. Next up, we want to do one last thing here. We want to put a comma and a 0, just to say that 0 is our default value, and then in parentheses. Okay, this means that once a point is recognized and it has a type attribute that becomes a variable, a type attribute that is equal to, let's say, 16. This delete node is going to delete all pieces except for the piece that has the class attribute corresponding to that. So it's only going to keep the piece that has the class attributes equal to 16 if the point is equal to 16. Okay, I hope that makes sense, but that's how it works anyway. So if you go here, we can see that we now have a lot of variation here. We have a lot of small, we have a big, and that's great. So we're almost done here. I'm gonna go to null. In here, we kind of want to also transfer over attributes. So we're gonna go to attributes, and we're gonna use template point attributes, which means that we're gonna transfer over the point attributes onto these geometries, which is all useful. Then we're gonna unpack them just to get back to geometries. Since our geometry is not that heavy here, it's fine really. They are no more than like 10 points per piece, so it's okay. And then we're gonna do a last thing here, kind of intersection hack, which is fine if it's like a far away distance, but for close up we kind of want to do some more elaborate things. But for this, it works. I'm going to do an interaction hack here with a point op, which basically, I'm not going to go over this, but what it's basically going to do is it's going to look at all the points, and if a point is lower than 0, it's going to transform it up to 0 in y value, okay? Dig into this, take a look at what's happening in here in the scene file, and I'm sure you're going to understand it. We can just take a quick look here. I'm taking a position, I'm comparing, and here I basically multiplied back, so yeah. And here I'm doing some kind of attribute. I don't know what I'm going to use this for, but never mind this. This is what goes out. This is a new position. So every point that is below 0 gets the position 0 in y. So if a point position is lower than 0 in y, it gets the position y. Okay, that's basically what happens here. And yeah, that's the end of this example. It sounded trickier than what it is, but I encourage everyone of you to like dig into this file and kind of look through this and see what actually is happening. Disconnect things, change things, and really go through this, because me talking is not gonna bring forward the knowledge in here. I think more digging through it will do that. So yeah. Anyway, thank you guys for listening, and see you next tutorial. Thanks. Bye.